2 years ago, I got the opportunity to come and speak to you, and it was great to be able to connect with everybody here, and actually to get the swag. My favorite part of this event is I got a raincoat last time because we were in London, and now I have a t-shirt for the summer as well. So I'm fully kitted up with the Linaro gear. Anyway, let's talk about Microsoft's involvement with ARM. We're going to do two parts to this. This is for software engineers, and so I've brought Pedro to come and do some demos for us. But first of all, I do need to talk about the Windows journey. Microsoft has been delivering Windows on ARM since 2018. But last year, with the Snapdragon X Elite from Qualcomm being released, we were able to launch our Copilot Plus PC range, which brings three key advantages to the industry. First of all, for our customers, it's aimed at bringing mobility, changing the game when you're bringing your laptop with you that has all day or even beyond all day battery life, all the things you need. It's quiet, it's cool, and it's powerful as well. The second thing Copilot Plus PCs is driving with the Snapdragon X Elite is that the ID that our device manufacturers create for our customers now has a huge range of available options with the reduced size of battery, the reduced size of components, and the reduced size of the heat dissipation that's required in them. So a completely new range and boundaries on the specs that we can have. But probably the third and the most important is bringing AI to the edge in the NPU that's inside of the chip that we're now shipping for Windows. And it's a very capable chip that comes from Qualcomm. 12 cores in the top spec range, 4 of which are actually efficiency, so it's bringing that mobility or that mobile experience into the desktop. So we've got the top-end performance, and also we've got the battery-saving capability in these devices as well. And what that's delivered in the industry is great devices from the top manufacturers across the industry. Asus, Surface, Lenovo, Dell, and so on. They've all got devices in this range that are powered by ARM software, ARM hardware, excuse me. Software is the next slide. So we've put a lot of effort in to bring the software ecosystem forward for Windows on ARM. But there are three projects I'd like to just call out from the last 12 months, which for me are standout game changers for Windows on ARM. The first one we've already had from Grant is GitHub Actions is now available running Windows on ARM runners. And so my call for you is to go and use those in your projects and to build for Windows on ARM today. The second one is PyTorch 2.7 shipped with ARM native support in April, which is bringing the AI workload right onto the device that you're using as your daily driver to go and build those AI workloads and deliver the applications. And the third one is completing the 3 top compilers with GCC 15.1 now has the rudimentals. It's the beginning of the journey for Windows on ARM support through that third compiler. We're not done. There's a lot more we're going to do. But what I want to do is stop talking about our momentum and actually excite you with a few demos, and Pedro is going to take us through that. Pedro.
Thank you. When I started in the kernel team a while ago, the way we did software development was for new hardware features, for new hardware CPUs, was very different. Tape outs were 18 months apart, and every hardware vendor did many tape outs until a CPU was done. We could fit a whole new feature development support in software for the operating system in an interval of 2 tape outs. So we could get the latest beta CPU, do all of the coding, and by the time the CPU hit the market, we were ready. Not anymore. Distance between tape outs, thank you TSMC, super short. And a lot of companies are doing 1 tape out. And all of this is thanks to simulation and emulation. All the hardware vendors are using RTL emulation far, far more. And NVIDIA would have been out of business if it wasn't for software simulation at some point. If you haven't heard the podcast on NVIDIA for Acquired, that's something I recommend. So we have to do the same thing. We don't have time to squeeze software development for a hardware feature in the middle of tape outs. So we have to use emulation. And if you know me, you'll probably assume that I'm going to talk about ARM64EC today, but I am actually going to talk about how we do pre-silicon engineering these days using emulation, whether it's fast models from ARM or using QEmulator, public source, open source project. I'm going to talk about QEmu, and that's actually how we do a lot of engineering, and I want to show you how we're improving the experience of QEmu for people that experiment, design, and test on Windows on QEmu. Well, Windows has a very, very rich, I'm going to start putting my readers on and off. This is a new experience for me. Windows has a very rich self-hosted debugging experience, and it supports a bunch of transports, serial, FireWire, USB, but the best one is by far Ethernet. And Ethernet only supports a handful of Ethernet cards, because obviously for a kernel debugger or a hypervisor debugger, you can't just use the normal driver. You have to use something that is really, really conducive to run in a Spartan environment of the debugger. And the first thing we did was to add support for kernel debugging and hypervisor debugging through the VirtIO NIC. So you can configure your VM to do kernel debugging and hypervisor debugging through the VirtIO NIC, giving the fastest, most experienced, efficient experience for debugging. But that's not all. Not everything can be debugged with self-hosted debugging. For example, you can't debug the VBAR with self-hosted debugging, because if you ever try putting a breakpoint on the code that handles breakpoints, that doesn't end too good. So QEmu also supports a GDB port that allows you kind of to pretend you're a JTAG, kind of like a hardware debugger, but virtualized. And there's a bunch of software that knows how to talk that protocol, GDB itself, obviously, and IDA, for example, but they don't offer like a very rich experience with Windows. Well, most of them don't know how to parse Windows symbols. The other half doesn't have that, all the extensions that you can use with a Windows debugger. So another thing we did was to add support to the Windows debugger to connect to that GDB server. In fact, we added support for connecting to GDB server ports from other hardware debuggers, such as T32 from Lauterbach. And you can have almost a seamless experience using a hardware debugger as if you're using the self-hosted debugger. And let's boot. I'm actually going to show this. So first, there we go. So first, I use WSL, Windows Subsystem for Linux, to build my TFA and my EDK2. And I transferred it to MSys2, where I'm going to run QEmu native on Windows on ARM on my two generation ago. I'm not even using a Copilot Plus PC. It's a 2 generation ago ARM laptop with QEmu running natively, a project that had immense contributions from Linaro. I'm going to hit it run. I'm going to bring my debuggers. Oops. And as the VM connects, as the VM starts, hopefully we'll see both the hypervisor debugger, sorry for the small print, both the hypervisor debugger and the kernel debugger should connect, and Windows should start booting. And by the way, this is all using software simulation, because the VM that I am starting uses hardware features that don't exist in the wild yet, like a 2 kilobit SVE vector. So I can go to my hypervisor debugger, break in, look at the call stack, Resume. I can break in the kernel debugger, look at the call stack, look at the disassembly, and it's super responsive, almost as debugging a user mode exception application directly. I can dump all the processes, which not that many by this time, and hit go. And of course, if I want to do that JTAG debugging, so I can go to the combat monitor, GDB server, and it tells me I need to connect to port 1, 2, 3, 4, and from the debugger, I'll show you. So here you have the experience. I'm really sorry about the font. Let me see if I can fix this. There we go. We have support for T32, OpenOCD, VMware, and of course, QEMU. So I can do localhost 1, 2, 3, 4, enter, yes. And I'm connected. I have JTagged in my QEMU VM. Of course, if you've used the JTAG debugger before, it doesn't know where it is. Obviously, it doesn't have all the context of, this is the kernel, this is the hypervisor. So I can use an extension to use a handful of heuristics to detect what the environment it is on. Hello? There we go. They found the hypervisor. So I'm going to have it load the hypervisor symbols. And here I am. And I'm even showing a part of the source. So you forget you saw that, okay? And there it is. I'm on the stack. So it's almost like a transparent experience. I'm using a hardware debugger with symbols, with extensions. I could dump every structure as if I was using a self-hosted debugger. I'm going to hit go. And now the VM is running again. I mean, of course, it's running in a software simulation. And everyone knows that booting Windows takes a long, and their software simulation takes a long time. On this laptop, it will probably take 40 minutes. We don't have 40 minutes. So if only I can make Windows smaller. Like smaller enough to boot in the contents of this talk. That would be super nice. It turns out I can. So this is the Windows you know. Very big Surface, Windows, desktop, client, and server. But there's one thing that has been in the market for a while, but it's very, very not well known, which is Windows run levels. And Windows run levels is a little bit like the run levels you know in Linux. You can tell Windows to only boot to a certain run level. So run level 1, there's multiple run levels. We actually use this in the cloud, and we use this in many of our sub-SKUs of Windows. But Windows 1 just gives you a basic console application support. No services, no RPC, no network, nothing. Just basic console. You can run a lot of tests in it. Windows 2, you get services, network, RPC on top of that, but still only text, no graphics. Windows 3, you get graphics. If you ever used the Windows PE pre-execution environment, pretty much looks like that. Windows PE is a little larger than run level 3. And then on top of that, you get desktop, client, and server. The Azure host is Windows 2. So it actually runs a very small version of Windows that boots very fast and is expendable. So with that, I can show you that, hopefully. Let's go back to the machine has booted by now. In fact, even on this laptop, fanless, and 2 generations ago, this VM boots in 1 minute, 48 seconds. And it emulated both the hypervisor, EL3 all the way to EL0. It would boot under a minute if I was emulating only EL1 and EL0. It's only kernel and user land. I can show you that is taking, well, that is taking 279 megabytes of memory. That hasn't been true for full Windows in a long, long time. So that is the end of my demo. Well, I ran out of time too. So, call to actions. How do you get WinVos? You go to Bing or Google, fine. You type WinVos, and that's your first hit. You download the ISO, and there's a bunch of scripts that you can use to create whatever run level you want. Creates a tiny little image, feed it to QEMU, boom, that's what you get, what you saw here. Also check out WinDebug, because as you saw, it has really cool new features. And run them all from your from your Copilot Plus PC natively, thanks to a lot of the contributions from Linaro.